Now we'll study what happens when metals react with water. This activity needs the teacher assistant collect the sample of the same metals as put small pieces of the sample separately in beakers half filled with cold water. So you can just read this activity by yourself again. This is the activity figure. Okay, we'll just start with the observations. Metals react with water and produce metal oxide that we already know, right? And hydrogen gas also. Yeah, this is one more hydrogen gas also. And basic or say metal oxides also, some metals oxides also react with bases to produce salt and water, and with acid as the same too. So metals react with water and non-metals react with also water. Sometimes they also produce the same effect. We'll read it on later, however. But all metals do not react with water. Metal plus water is equal to metal oxide plus hydrogen, and metal oxide plus water is equal to metal hydroxide, right? Because metal oxide already contains water, as we can see that metal plus water gives metal oxide and hydrogen. Maybe hydrogen is left out somewhere, and oxygen from the water is taken by the metal and water is left out, or hydrogen is left out to be precise. Hydrogen molecules are left out, and the oxygen molecules in water react with metals to produce metal oxide. When metal oxide reacts with water, then it produces metal hydroxide. Why? Because metal oxide already has the required number of oxygen molecules, but we are adding excessive, we are giving it excessive hydrogen and excessive oxygen. In the first case it was rejecting hydrogen as it was, but in this second case we're giving it even more hydrogen, more oxygen, so it has no other choice but to combine with it and to form metal hydroxide, which contains metal plus hydrogen plus oxygen. Now metals like potassium and sodium react violently or vigorously with cold water. In case of sodium and potassium, the reaction is so violent and exothermic. I've told you previously that exo means heat is given out, right? Exothermic reactions are those reactions in which heat is given out. So violent and exothermic that the evolved hydrogen immediately catches fire. Okay, so that this hydrogen that is evolved immediately catches on fire. Alright, so if you put like I told you previously, if you put a sodium cake into water or with cold water, it will put on fire, it will immediately catch fire. Have you ever heard about this, putting something in water and so it catches fire? Right, so ironic. Water is used as an extinguisher, but in the case of sodium or potassium, water is used to make fire. It's used to create it. So 2K, that is 2 potassium plus 2 H2O, 2 molecules of H2O water, it will form potassium hydroxide plus H2 hydrogen plus heat energy. As I told you, it will release a lot of fire, so it would be heat energy. Then sodium, this is sodium, right? That was potassium, this is sodium now. So sodium plus water is equal to sodium hydroxide plus H2 plus heat energy, the same reaction. The reaction of calcium with water is less violent. The heat evolved is not sufficient for the hydrogen to catch fire. So it is not so much exothermic that the hydrogen will catch fire, though it is a lot exothermic still. So calcium plus hydrogen forms calcium hydroxide. We have read this reaction previously in acids, bases and salts. So calcium hydroxide is, I guess, slaked lime, right? So calcium starts floating because the bubbles of hydrogen gas formed stick to the surface of the metal. So the reaction is somewhat like this. I'll tell you. This is a beaker full of water, right? This, we put calcium into it. We're putting calcium into this, and there's water all around. The calcium reacts with water and hydrogen starts releasing out, but hydrogen bubbles still stick to the surface of this material, like of this metal. They still stuck on to the surface of the metal. So the metal is completely surrounded by bubbles, and the bubbles will obviously make it float, make it come out on the surface of the water and float over it. Alright, the bubbles will decrease the weight of the metal and make it float over water. Magnesium does not react with cold water, it reacts with hot water to form magnesium hydroxide and hydrogen. Like in this case, calcium hydroxide, it will form magnesium hydroxide plus H2 and hydrogen, same. It also starts floating due to the bubbles of hydrogen gas sticking to its surface, right? As expected. Metals like aluminium, iron, and zinc do not react either with cold or hot water, but they react with steam to form the metal oxide and hydrogen. So you can see how many different kinds of reaction there are possible with metals. Some react with cold water, some react with hot water, some don't react with any kind of water but with steam. That is also a form of water. So metals, like you can read the reaction by yourself. It's not a very difficult reaction. It's just aluminium plus water forming aluminium oxide plus hydrogen. The same goes for the second reaction. Metals such as lead, copper, silver, and gold do not react with water at all, right? So you put a chain of gold into water, what will happen? Nothing will happen, obviously. You put a coin of copper or silver into water, nothing will happen, right? What happens when metal reacts with acid? Now, what will happen if a metal reacts with acids? As we have read about a particular kind of metals, what was its name? I don't remember the name. I think it was somewhere here. Amphoteric oxides. So we've already read about how amphoteric oxides react with acid to form salt and water. As we have already read the reactions of metal oxides with acids. So I guess the case would be similar here too. Let's see. You have already learned that metals react with acids to give a salt and hydrogen gas, right? Salt and hydrogen gas. Sorry, I keep on saying water. They actually release salt plus hydrogen gas. So metal plus dilute acid. Dilute acid means it's already mixed with a little bit of water. It's not undiluted, it's not pure acid, it's mixed with water or something to decrease its concentration, to decrease its power. But do all metals react in the same manner? Now obviously this is the thing to find out, since we've seen how many kinds of exceptions there are between metals and non-metals. So again, you can read the activity by yourself. I won't be wasting time by reading the activity. Write equations for the reactions of magnesium, aluminium, zinc, and iron with dilute hydrochloric acid. Hydrogen gas is not evolved when a metal reacts with nitric acid. So hydrogen gas is not evolved when metal reacts with nitric acid. However, this is again an exception. It is because HNO3, that is hydro or nitric, I don't know what it is. This is maybe a nitric acid or a hydronitroxide, something like this. Is a strong oxidizing agent. It oxidizes, it means it gives oxygen atoms to the H2 atom, right? It provides the oxygen atom, it gives oxygen to H2 atoms, that is hydrogen atoms produced to water. And obviously when H2 atoms or hydrogen atoms combine with oxygen atoms, they will produce water, and itself get reduced to any of the nitrogen oxide, and then it will be reduced to nitrogen oxide since it has given oxygen atoms itself. So what let's lead now. But magnesium and manganese, and most people I think make this mistake, they often read manganese as magnesium too, or maybe they think that it's written, it's a mistake. These are two different elements, magnesium and manganese. These are two different elements. React with very dilute HNO3 is I think nitric acid, but magnesium and manganese react with very dilute HNO3 to evolve H2 gas. Now they give out H2 gas, yeah they do, but in the previous example as we saw, hydrogen gas is not released. But these two are exceptions again. Magnesium and manganese do give out hydrogen gas even while reacting with nitric acid. So the rate of formation of bubbles was the fastest in the case of magnesium. The reaction was also the most exothermic in this case. The reactivity decreases in the order. So this is all obviously based on the reactivity of the metal, right? How highly reactive the metal is. There's a complete table given of, see here this table is. So the most reactive metal is potassium, in the second it's sodium, then calcium, then magnesium is also very highly reactive metal, as we can already see. And the least reactive metal is gold. So in the case of copper, no bubbles were seen and the temperature also remained unchanged. And why is that? Because copper is not so reactive. Okay. This shows that copper does not react with dilute hydrochloric acid. Now obviously if you put potassium with dilute hydrochloric acid, I think it would just give out a kind of bomb, like boom. It would explode most probably, I think so. Aqua regia is a freshly prepared mixture of concentrated hydrochloric acid and concentrated nitric acid in the ratio 3:1. It can dissolve gold, even though neither of these acids can do so alone. So you can clearly see how powerful this acid is. and Latin for aqua regia in Latin for means royal water, and it is highly corrosive fuming liquid. So most probably the kinds of liquid you see in movies, like liquid spatters on the building or on the ground, starts bubbling up and giving off fumes. That's aqua regia. Maybe not, but that's what aqua regia actually looks like or does to the materials it comes in contact with. It is one of the few reagents that is able to dissolve gold and platinum. So how do metals react with solutions of other metal salts? Again, the activity is for you. You can read it on your own. Reactive metals can displace less reactive metals from their compounds in solution or molten form. So if the metals are in solution form, in liquid form, or molten means पिघली हुई, molten form, then they can replace the less reactive metals from their compounds and instead take their place. We have seen in the previous sections that all metals are not equally reactive, as we can again infer from this table. We checked the reactivity of various metals with oxygen, water and acids, but all metals do not react with these reagents. So we were not able to put all the metal samples we had collected in decreasing order of their reactivity. Displacement reactions studied in chapter 1 give better evidence about the reactivity of metals. It is simple and easy. If metal A displaces metal B from its solution, it is more reactive than B. So metal A plus salt solution of metal B will form salt solution of A plus metal B. So this metal A is more reactive than the metal of which the salt solution is made up of. So this metal has displaced this salt solution, right? So now it has become a salt solution of metal A. And what has become the metal? The metal has become of what the salt solution was. So simply they have interchanged positions. That's all you will have to know. And the reactivity series, let's see how big the reactivity series, whether we'll need to cover it up in the next video. No, I don't think. The reactivity series is actually very short. Reactive series is nothing but actually a kind of series which displays metals from most reactive to the least reactive. The reactivity series is list. It is a list of metals arranged in the order of their decreasing activities, like how active it would be when it reacts with another substance. So this is the reactivity series, how active the metal would be. After performing displacement experiments, the following series known as the reactivity or reactivity series has been developed. So this series has been developed by scientists after lots of experiments and displacement reactions, right? So in the next video we'll covering how do metals and non-metals react.